Welcome to Secure Software Development. We're going to begin the same way we always begin, in the year 1961. Now, not much is going on in 61, right? It's kind of a boring year unless you happen to be involved with the compatible time-sharing system. When you think about 1961, boom, that's what comes to mind, the compatible time-sharing system. The idea for a time-sharing system, the idea that I could take a computer and I could break it up into chunks, and I could share those chunks with multiple users or multiple programs, or maybe even create a virtual machine out of each chunk. That was a cool idea. It wasn't new. John Backus had that idea in 1954, and the problem was computers, well, they weren't super powerful, and no one really knew how to do this. There's a lot of things that have to come along to make this kind of thing possible. And they all finally came together in the super powerful, for its time, IBM 7090. And now they say, hey, I think we have something where we can actually implement this idea of time sharing. So they reached out to Fernando Jose Corbato. There's a picture of him over at the right, to lead this effort. He was later, in 1990, awarded the Turing Award for his work on this project. Pretty cool stuff. Well, here he is in 1963, working on the time-sharing effort. And this led to a whole bunch of stuff. The original chatbot, Eliza, was created here. That's the first one, right? The ancestor for ChatGPT and everything that came after it. Passwords. I mean, think about it. Before this, a machine was at any given time on a single purpose. It was running one program for one user. You didn't need passwords. But now, with lots of people sharing the machine, you need some way to manage access. Passwords come along. In addition, people can now have accounts on the machine and do stuff and perhaps receive electronic mail. So that comes along. Likewise, instant messaging. QED is the predecessor for ED, which is the predecessor for VI, which is the predecessor for the editor that we all use exclusively and never use anything else, Vim, right? Everybody uses Vim. No one uses Pico or Nano or Emacs, oh my word, or any of the other editors out there in the world. Virtual machines, right? The whole concept here is a virtual machine. And of course, time sharing. If you'd like to watch a video about Corbato explaining what's going on, you can. He was interviewed by one of these MIT reporters, and it's really just fascinating to hear him talk about the state of computing in 1963. Later on, they'd produce a report, right? The Compatible Time Sharing System 50th Anniversary Commemorative Overview. This was a major milestone in computing. And so people went back, they took a hard look at what had happened, and they wrote about it. And there's just a lot of interesting stories and information in this report. Ultimately, the CTSS, Compatible Time Sharing System, supervisor provided virtual machines. So that you had a big 7090, which was then divided into smaller 7094s, and each user got their own 7094. It had one special virtual machine that had actually all the hardware, the tape drives and so forth associated with it. And it had a file system, and of course everybody had to have their own files, and so you had the home area, right? There's not a home area on a Commodore 64. There's not a home area on an Apple II, and there weren't home areas on machines prior to this, but now there are. Okay? If you'd like to play with it, there's a simulator available online, because of course there is. And that obviously takes us to Adam Scherr. I know you were wondering when we were going to get to him. Here he is. Adam Scherr was a computer science student. He was studying the performance of CTSS, and he would later win the Grace Hopper Award for his work. And that's important. Put a pin in the fact that he wins an award for the work he does studying the performance of this machine. And that takes us forward to 1965, another dull, boring, humdrum year when basically nothing is happening. Except Cher is doing some stuff. Cher is doing some stuff on the machine. That's clearly the most exciting thing of that year. And in the 50th anniversary report, he recounts an interesting story. There's this additional note, and I think it's worth taking a look at. He says, there is an incident that I confessed to on the 25th anniversary of CTSS and Project Mac. His PhD research involved measuring, modeling, and simulating the performance of the system. Okay? He had a lot of stuff he needed to run on the machine in order to collect data to then do his PhD, for which, let me emphasize, he would later win an award. The actual scheduling program that was the heart of the operating system was part of this simulator. He created a simulator to allow him to run these experiments. He needed many hours of computer time to run his simulations. So since he needs many, many hours to run these very important simulations that are necessary to the sponsor, that will win him an award, that will get him his PhD, what do they give him? They give him 4 hours of processing time per semester. Okay, well, that's not enough, right? That's not enough. So he immediately exceeds that, and he hasn't really gotten any work done. And now he'd be stuck waiting for the next semester until another 4-hour increment came along and he could do more work, right? No one had a sense of how to allocate this stuff. Because I had embedded measurement code into the operating system, I had access to the listings of the system. I discovered that the cumulative time usage for each account was loaded into the operating system every time the associated user's image was swapped into memory. So every time your little virtual machine gets swapped in to run, your total time usage is loaded in as well. At the end of the time slice, the usage was updated, right? How long have you been on here? I will add that to your total usage. And then you were swapped out. I added an XEC indirect execution instruction to the performance measurement code I had in the operating system so I could indirectly execute a store zero instruction to zero out my usage anytime I wanted to. See what he's doing? It swaps in, and in the image that you are given, right? So in your little virtual machine is also the counter for the amount of time you've used. So that's in your memory space. It's not stored somewhere else inviolable in the machine. It's stored right there in your process space. So he would then zero it out. So I would rack up usage time until I got close to 4 hours, then zero it out and start all over. Because again, he needed to do this work. This worked well until the spring of 1962. What happened was that someone on the CTSS staff, I think Bob Daly, another person who's sort of well known, came to me and said that the space my measurement programs used was needed. And since I was done measuring, right, I mean, you basically used up almost all your 4 hours, you must be done. They were going to remove my programs from the operating system. At the same time, my privileges to modify the operating system were revoked. Okay, so now he's lost the ability to plug in his stuff and zero out the usage. Being desperate, I had to find a way to regain access to the operating system so I could reinsert my code. All the passwords for the system were stored in a file called uaccount.secret. The .secret is what really sells it. That's what makes it unreadable, the fact that it says secret. Under user M1416. There was a way to request files be printed offline by submitting a punch card with the account number and the file name. Late one Friday night, I submitted a request to print the password files, and very early Sunday morning, if anyone finds it and can grab it, I went to the file cabinet where printouts were placed and took the listing out of the M1416 folder. So now he has all the passwords. I could then continue my larceny of the machine time. Now, this is the part I think is delightful. This is what changes it from just being I found a way around the system because I had to do my work into an actual computer science student, and I would have given him the Grace Hopper Award for this part alone. I did two things to spread out the risk. First, I contacted JCR Licklider. Now, he is the ARPA administrator for the project. All right, he's the guy who's funding it. Because I was interested in computer security, I tempted him by offering a copy of the system's passwords. So he's like, hey, I've got a copy of all the passwords to the system. Would you like to see them? And he's like, oh, yeah, I would like to see those. Well, then I want immunity. So after being granted immunity, I told him what I was doing and sent in the password files. He told the program manager what he was doing, sent in the password files, okay? And, here it comes the best part. I later learned that he had used the passwords to log into Fano. He's one of the project managers. Log into his account and maybe others and leave taunting messages. So you're an ARPA program manager. You're running this super Gucci computer project. And what are you doing? You're trolling people. I love that. That's just delightful to me. The second thing I did was tell two other struggling PhD students how to get more time on the system. One was Don Carroll. He was an assistant professor in the Sloan School. And the other was Peter Denning. So Denning is another seminal figure. You can go and look him up. Both were doing simulations. Don of job shop scheduling and Peter of disk-based systems using the simulation software I developed for my thesis. Okay, one night Bob Daly noticed someone logged into the system. Every time a login occurred, the ID was printed, and he knew this person wasn't there. So he's like, hey, Jimmy's just logged in, but I know Jimmy's not here. What's going on? He almost caught the person doing it. After some investigation, Bob figured out the culprit had modified code that I'd left in the system, but he couldn't figure out why there was an XEC being inserted, and I didn't help him figure it out. I finished my simulation work in May of 1965, right? That's why you know about 1965, because you're like, oh yeah, that's the year he finished his PhD work. I know. I think of it the same way. And then I left for IBM. Later, I heard that Don Carroll had been caught and called on the carpet by Professor Fano. I ultimately had the opportunity to confess to Professor Fano in person at a 25th anniversary get-together. This is the 50th where he's writing it. He assured me that my PhD would not be revoked. So as soon as you introduce a multi-user computer, I mean, not just introduce it, but are in the process of creating it. As soon as that's there, as soon as there are passwords, as soon as you try to have security, boom, immediately it gets in the way of someone getting their work done and is broken. So what can we should try to learn some stuff from this. And one of the things is this principle of desire paths. So over on the left, you see a little picture, and you can see there's been a lot of walking. We used to call these deer paths when I was a kid. Around the National Lab, they call them goat paths, I think, because they don't want us to do this. But ultimately, people create these desire paths because it just makes sense. You're like, oh, look, my car is right there, and I'm here. I could walk all the way down to the corner, go around the corner, walk all the way back up here, or I could just walk right there to it, okay? And if it's such a common thing that everyone wants to walk that way, you will get one of these paths, right? You don't get it because one or two people walk that way occasionally. You get it because everyone can see that that is the way they should be going, okay? And that leads to this, what we would call a desire path, right? This is the case where you've laid out sidewalks and said, here's where you should walk. But people aren't stupid, right? People are smart, and they can go, it's faster to walk there, and that's what I'm going to do. The implications for software development are maybe obvious. I'm not sure. Sometimes insiders are just people trying to get their work done, okay? And if you create a situation that requires people to break the rules in order to get their work done, surprise, they're going to break the rules. They're going to figure it out, especially if they're insiders who understand the system. And that knowledge can be spread, right? This guy wasn't the one that had the knowledge. He told it to two other people. He gave the passwords to someone else who then used them to troll, right? If you create a situation where people have to break the rules to get things done, they'll break the rules. They'll share that information, and it might lead to circumstances that you don't want. Okay? So consider special circumstances and maybe add methods to address those. But above all, talk to your users. Okay? Find out where they have friction with your system and where they may have to implement workarounds. I've got stories about that I will tell in class, but there's plenty of examples where just talking to users has led to changes in configuration, led to changes in options, led to changes in the way programs work that make systems much more useful, that make them much better without a significant change. When I worked for CTI, later Siemens Medical Imaging, we made some minor changes in the way a reporting tool worked. It just changed some configuration stuff. That's all. We just didn't modify any code. We just made some changes to the configuration file. People loved it. They thought this was a major upgrade, even though all we'd done was change the out-of-the-box configuration of a few systems based on instrumenting the code so we could see how people use it. Right? They'd open the report tool. They would immediately do the same thing every time. And we're like, oh, they're changing a bunch of options. We should just make those changes the default. Great. Don't fight desire paths in your system, or people will explicitly subvert the system to get things done. You may say, this is the way you ought to do it. Do it this way. You need to do it this way. People they're not dumb. They're going to figure it out, and they're going to figure out other ways to do it. And by fighting them, you're encouraging them to do that. So let's talk about a quick aside here. So this came up in some discussions I had with students, and I think it's worth highlighting more generally. And that is our old friend, the halting problem. So a lot of you have had a computing theory class. You've talked about the halting problem, and you have a sense of what it means. And maybe for a couple of you, it's not quite the way you should be thinking about it. So sometimes people will talk about reducing a problem to the halting problem. And you'll see this even sometimes in the literature. And the idea is I've got a problem P. And what I can do is I can reduce, quote unquote, reduce P to the halting problem. And, well, I know the halting problem is undecidable. And since P got reduced to it, P must also be undecidable. So be really careful with this line of thinking. So as an example, look over on the right. Let Q be a Turing machine that adds 2 and 2. Let's let P be another Turing machine that simulates Q and, if it produces 4, enters an infinite loop. Otherwise, Q halts. You get that? So to figure out if 2 plus 2 is 4, we need to determine if Q halts. That's the halting problem. So clearly adding 2 and 2 is undecidable, right? This is absurd. This is an absurd example. So don't think like this. That's not the right way to think about what you're trying to do. The way you should think about it is maybe reducing from the halting problem. So we're given a decision problem P, and we want to try to show that P is perhaps undecidable. And so we reason as a proof by contradiction typically. We assume P is decidable, and then we proceed with the proof by contradiction. So here's let me fill in some background for you, right? When I say proof, I mean a convincing argument, okay? And when I say the halting problem is undecidable, I mean we have been convinced at some point that the halting problem is undecidable. If you haven't been convinced that the halting problem is undecidable, this may not work for you. So, there's a lot of really good, solid, convincing arguments that it's undecidable. And we want to construct a similar argument that our problem P is undecidable. So here's how we work. We use P to build a system that solves the halting problem, right? So what we're saying is, I'm going to build a system that solves the halting problem. And every piece of the system that I'm building is something that I believe I can make, and that I can convince you I can make. And I can convince you that the entire system will work, given all the pieces, and solve the halting problem. But wait, you're convinced the halting problem isn't generally solvable. That means something must be wrong in my construction. So you go back and you look for the flaw in my construction. And if I've been careful with my argumentation, with the design of my argument, the only place that flaw can occur is in my assumption that I can solve P, that I can decide P. And that means, since I believe the halting problem is undecidable, I believe the construction is valid, I believe that all the other pieces of my proof are valid, the only thing that could be wrong is P, and so P must be undecidable. I hope that makes sense. What does that look like in practice? Well, let's pick on a very mathy case and take a look at that. Let's say we have a Turing machine M, and we have some non-empty set S, and M draws its inputs from S. We further assume there are some things in S for which M will halt, and there are some things in S for which M will not halt. Okay, and maybe it's true that it halts on everything. Maybe it's true that it never halts. Maybe it's true it's a mix. We don't necessarily care, but we define a new set L as a set of ordered pairs. Okay, and the ordered pairs look like Mn. M is the machine, and N is just a number. It's a natural number which says M halts on N or fewer inputs. So, for example, let's assume that M always halts. Okay, in this case, we need N to be basically infinite. Assume that it never halts. In this case, N can be 0, or it could be 7, right? Halting on 0 inputs, 0 is clearly fewer than 7, so there you go. Now, the question is membership in L decidable? Can I give you an ordered pair of a machine and a number, and you tell me something about it? Okay? By decidable here, I mean, can you construct basically another machine that when I give it the input, let's say some Turing machine and the number 5, it's going to tell me if that ordered pair is an L. Now, it's fine if it works on some, but not others, right? That's not a full decision procedure for L. That's a decision procedure for a subset of L, and a subset of L can be decidable. But I would contend that the membership in L generally is not. So let's take a look at this. Here's how we'll reason. Let's assume that I do in fact have a machine that can decide L. Let's talk in the language of code. I've got a function that I wrote in Rust, and I call it with M and N, and it comes back true or false to tell me if that's in L. So I wrote that code. Elsewhere, I wrote some code, and what that code does is, given the Turing machine M and the input A, I want to decide whether M halts on input A. So I have a new function. This new function takes M and some input to M, A, some string that will go onto the tape. And it builds a new machine that ignores the input, and writes A to the tape, and then it simulates M. So just keep up with this for a second. M prime is going to write the initial stuff to the tape. It's going to write A to the tape. It's then going to simulate M, so it's going to run M on input A. So let's ask about what we have so far. Do we believe the stuff we have so far can be done? Do you think you can create a Turing machine that writes a string to the tape? Sure, that seems doable. Do you believe you can make a Turing machine that simulates another? You should, because that's how we originally got the proof of the halting problem. So yeah, we can do these two things. You should believe that we can. Okay. Now, we run the decision procedure for L with the input M prime, our new machine that halts if M halts on A and doesn't halt if M doesn't halt on A, and 0. Right? What are we asking? We're asking, does M prime halt on 0 or fewer inputs? Okay. We're asking, does M prime ever halt? So if I can run that decision procedure and it comes back and says, yes, I know M halts on A. If I run it and it comes back and says, no, I know M doesn't halt on A. I hope that makes sense. Now, because we're convinced the halting problem is not decidable, and we just built something that solves the halting problem, we have to conclude that something is wrong. And again, our construction all seems valid, something we can do. The only place we have some room to say, no, you can't do that, is this mysterious decision procedure for L, so we conclude that L is not decidable. This is the correct way to apply this kind of reasoning. So is it possible to decide if a pair is in the set L? Well, suppose I give you a Turing machine M star that ignores its inputs and just halt. Well, M star 0 is not in L for any positive n up to the size of S. So, yeah, I can tell you immediately something about that one. Suppose I give you a Turing machine that ignores its input and just runs forever. Then M infinity n is in L for any n. So, yeah, some of these are in fact decidable, right? I know that for the machine that just halts, I know that M star 0 is in L. For the machine that never halts, I know that this whole collection of M infinity n pairs is in L. So I can decide that for some pairs, but I can't do it for any arbitrary pair. That is, the problem is undecidable in general, but it may be decidable for particular cases. And in fact, it's often the case that there are important subsets of undecidable problems that are decidable, right? The set of all computer languages, all computer programs, let's say it that way, all computer programs, and whether they halt, that's undecidable. But the set of all regular finite automata, that everything is decidable for those, and that's a subset of this larger collection of things. So let's talk about trust and its many discontents. There is Ken Thompson. So I would recommend that you go off and read Ken Thompson's short paper, Reflections on Trusting Trust. I think it's really good. I think it's worth reading. He is a Turing Award winner. He was one of 2 people who created Unix and C. You should go and read this paper. It's from his Turing Award lecture. I think it's really good. There's a Russian proverb. I'm not going to try to pronounce that. My son could read that to you, but I'm afraid I cannot. The best I can do, I got him to tell me, it sort of sounds like this: Dovrye no provrye. And it is trust but verify. So we don't owe that to Ronald Reagan, right? That's an old Russian proverb. And let's ask the question, what if we don't do that first thing? What if we don't trust? What if we only do that second thing of verify? Okay? And we've actually talked about this before. Before I said we want to minimize trusted things, but maximize trustworthy things, right? That's a basic principle of security. Minimize the trusted things and maximize the trustworthy things. Minimize trust, maximize verification. Let's talk about the perimeter. So I want to protect my network, right? I want to protect my network. And so I have a natural trust boundary. I built the network, so I trust what's inside it. I trust the people who are there, the machines, the software. I don't trust things that are outside of my network, right? Outside the perimeter, there are threats. So there's us and there's them. And I believe all of the threats are outside my network, and I need to keep them outside my network. So that's my starting position. I've got a pristine, beautiful, perfect network. The threats are outside my network. Keep them outside. So I identify a perimeter and I build perimeter defenses, right? I build walls and moats and all the other usual things we think about. I build the wall. My network assets are inside the perimeter and the threats are outside. And that's just how it's going to work, right? I mean, you can't get over a wall. I mean, maybe if you had a ladder, but there you go. And now people come to me and they say, I want to work from home. Now, your home is not inside my network perimeter. Your home is outside my network perimeter, and that's where the threats are. So my initial answer is no, you cannot work from home. But then the CEO comes along and says, I want to work from home. And my answer has to be, yes, sir. So I have to implement some way to allow them to work from home. And so what I do is I extend the perimeters to something like a virtual private network. I have a trusted connection, and while your machine is connected to our network, I isolate it from other local network stuff. Or I require additional configuration. I require that you run certain software on it in order to connect, right? This is posture assessment. So now your machine can be in the network, but it's okay. Threats are outside the network. When your machine is inside the network, we've already checked to be sure it's safe, and then maybe it goes back out, but then before it comes back in, we check it again. Okay, I'm still trying to live with the idea that threats are outside the network. Now people come to me and they say, why can't I get to this thing with my phone or my tablet? Right? You want to bring your own device. BYOD. Well, you can't do that. You can't add your phone. Or wait, you're the CEO? Oh, well, then I guess, yeah, I'll have to figure out how you can add your device, Mr. CEO, or the president, or the VP of sales, or the assistant to the CEO, right? The CEO may be one thing, but he's hired some junior assistant just out of college, and he wants this guy to have his devices on the network. Okay, I guess. Or maybe you're just the guy who decides if people can add their phones to the network. Okay, so you get your phone added too, right? Well, I make you install stuff on your phone, and once you've done all that, then I say, okay, we can trust your device and you can join our network. Again, threats are outside our network. I think it's getting harder for me to believe that this is true. Now, suppose the threat gets into our network. That's bad. The threat gets through the perimeter, and now they're in the network. I have built all my defenses with the idea that I will defend the perimeter. I don't build defenses internal to the network because I want to facilitate people getting their work done. So if you want to print, just connect to the printer and print. If you want to get to a file share, just connect to that file share, right? You're inside the perimeter, so you're trusted. But now I'm getting a little bit suspicious of what's inside the perimeter, and I'm worried. Once a threat gets inside the perimeter, it can move around. We call that lateral movement, and it can threaten the whole network. And I have to admit at this point, there could be some threats in my network. So what's my next strategy? Segmentation. So I say, some threats are inside my network, but the threats are outside this inner perimeter. I have a much more sensitive perimeter here, and maybe there are some threats that make their way in here. We'll try to find them and get rid of them. Most of the threats are out here in the world, but there's none inside here, and so that makes lateral movement into this section hard. I have new trust boundaries, and it's harder for threats to cross these explicit trust boundaries, so I've reduced lateral motion. What is that guy? Look over there. There's some guy. He's in this. So people are crossing the trust boundaries with their devices? All right, so I don't know where I trust anymore, right? I mean, it's clear at this point, it's blindingly clear to me, and I kind of have to admit there can be threats inside my network. I just have to admit that. In fact, this was always a comfortable fiction, right? The idea that I could keep all the threats out with these perimeter defenses, that was always a comfortable fiction. Maybe sometimes it was true, but it was always more aspirational than it was reality. And now I'm confronted with the fact that people are running all over the place with their devices, they're connecting, they're doing other stuff. The threats are clearly inside my network, and I have to deal with that. How do I deal with that? Well, I need some definition of trust. And ideally, I want it to be three things, right? Because I've got to implement it. And I, as the IT guy who has to implement it, I need it to be actionable. I need to know what to do. Tell me what I do to get this definition of trust working for me. Programmable. I want computers to do this, right? I don't want to run around and you want to log in. That requires me to go there and do something. No. I want this computerized. I want it to be a programmable definition of trust. And if you can't get your work done using it, you are going to scream at me. And if you're the CEO or the president or the assistant to the president or my boss, it's going to be a bad day for me. So I need it to also be useful to all the different purposes I need. So I need to be actionable, programmable, and useful. That's what I need for my definition of trust. If it's also true, that would be nice. But, that's not something that I am going to care a whole lot about, right? The point is, our usual human notion of trust isn't necessarily going to work, right? I've known Aisha for 10 years. I trust her. She's fine. I can't program that. Maybe that's actionable, but I can't program it. It's not useful either because I just onboarded Terry, and Terry's working with Aisha on a project. Do I trust Terry as much as Aisha? I've just met him. I don't know. So this is a challenge. So let's shift gears a bit and let's talk about authentication and authorization. So authentication is the process of figuring out if someone or something is who they claim to be, right? And this happens all the time, right? You look at your phone to unlock it. The phone looks for landmarks on your face. If it finds them and everything looks right, it unlocks your phone. Maybe you use your fingerprint to unlock your phone. Maybe you use some other method to do it. But there's some way of saying, hey, I'm going to offer some proof that I am who I say I am. And then you'll let me in. Maybe I have a password or a PIN or a combination of things. Right? I am authentic. Same thing for machines. Machines authenticate to each other all the time. Right? When you SSH into a machine, you might see that thing that says, hey, this is the first time you've connected. Here's the host key. Is this right? So you're being asked to help authenticate the remote machine. And then you can store that in a database, and then the machine can be automatically authenticated in the future. Programs do this. Machines do this. Your web browser does it with websites, etc. Right? The site says it's google.com. And as proof that it is authentically google.com, it offers you some information based on a certificate chain, and you're able to then verify that back to a trusted root certificate, ideally. Authentication systems aren't perfect. They're all subject to being spoofed in some way. And that goes for all of this. Fingerprints, DNA, facial recognition, retina scanners, all these things can be spoofed in some way. And if you'd like to read about some of the shortcomings in forensic science, there's a great report over there from the National Academy of Press. If you'd like to know how to break some of these, the Mythbusters did a great job of looking at how to bust fingerprint readers. They tried some really clever, smart, high-tech methods, and those worked. They tried some really dumb, silly, low-tech methods, and those worked. It's a fascinating little clip to watch. You might want to watch that. The basic idea behind authenticating is you give a system or a person or something else that needs to know that you're authentic three things. Typically, it's something you know, right? I know my password or my PIN. It's something you are, right? Your fingerprint or your facial structure or the patterns of blood vessels in your eye. You give it some biometrics. And something you have. Maybe an RSA token, maybe a soft token on your phone, something like that. So something you know, something you are, and something you have. We usually don't require all three, right? Your phone often unlocks just with biometrics, okay? My password reader will often unlock with just biometrics. Occasionally, it requires me to re-enter my password to re-authenticate under certain circumstances. When I connect to the lab, I have to use my token and my password in order to get in. So combinations of those are very common. And all of this stuff, all of the things I'm talking about, passwords we already know. We already know passwords and PINs, right? We saw what happened with the door lock from last time that let the Girl Scouts come and get us. We saw what happened with passwords. The report will tell us this when biometrics fail. Will tell us about why biometrics can fail us. And RSA tokens, I mean, those could never let us down. But sure enough, if you go and read about the RSA hack, yes, even that stuff can let us down. All of these things can be spoofed or broken in some way. So let's talk about authorization. Authorization is the process of figuring out whether or not a person or a machine or a program is permitted or maybe is explicitly barred from performing an action, right? We want to determine the action is authorized, right? Like obtaining a license for your pet fish. There's a clip from Monty Python over on the right-hand side of that. Think of is authorized as a relationship between subjects and objects and actions, okay? So is this computer allowed to join the domain? It's got to communicate with the domain controller and exchange credentials. Am I allowed to use this printer? Well, I've got to send my credentials over to see if I can use it, okay? Some actions may create new objects. Those objects may then have their own properties, and we can sometimes get around this by chaining together actions, but that's a whole other topic. And now it's everyone's favorite time. Who doesn't love acronym time, right? Otherwise known as AT. There are a lot of authorization policies, and we've actually talked, I think, about some of these already. Mandatory access control, we've actually talked a little bit about. This is where I have a centralized, top-level set of definitions for who should be allowed to do what. I define a set of security policies, and I permit access if there is a specific, predefined set of conditions met. So mandatory access control, or MAC policies, have a top-down nature to them. And that's great because they can't be tampered with or overwritten, and it's terrible because they're not flexible and adaptable. Discretionary access control, a little bit better. This moves some of those decisions down and says, hey, you're the owner of this file. You should be allowed to decide what happens with it. And so this allows data owners to define authorization policies for their data and for data shared with them. We've distributed control a little bit. Then there's role-based access control, where access is based on your job function or your assigned privileges, okay? Right? I can do certain things, but I'm not in the IT group. If I were in the IT group, I would have other kinds of access, right? Not necessarily a superset, but a different set. I have some of the same things, but I'd also be able to get into the IT's private Git server, into a bunch of other stuff that I, as a general user, not in IT, can't do. And then there's attribute-based access control, ABAC. It's a bit of all the above, right? Authorization policies are based around a set of context variables, right? Attributes like roles and privileges, IP address, time, date, phase of the moon, action taken, right? The zombie alert level, all of these things are fed in, and we say that based on everything I'm seeing right now, this is whether this determines whether I should allow this action or not. And that does make some sense, right? Sometimes IT has information about, let's say, an ongoing set of attacks, some campaign that's taking place. And so they might disallow certain options because it breaks up that attack. And so it can change, the context can change for things beyond your control. Roles and privileges. Okay, here's how things are usually defined. This is not necessarily how those things are actually used. A privilege is the smallest unit of authorization that we want to control. It might be reading a file, writing a file, listing a directory, adding a user, deleting a user, printing something. Privileges should be, but are not always, disjoint. And what I mean by that is, suppose the privilege is you can print a file. Well, I got to be able to read the file. That implies I can read the file. It implies I can write to the spooler directory. It implies that I can execute stuff. There's a whole lot of implications to saying you can print. Okay? And so that may imply many others. A role is a collection of privileges, right? So the IT person has a certain role, and that gives them a set of privileges. I'm not an IT user, but on a project, I have a different set of privileges related to what I'm doing on that project, okay? And so forth. And many times people will use privilege when they might mean role. For example, we may talk about privilege escalation, but we often may mean role escalation, right? I'm going to somehow get access to an account for an administrator and be able to do the stuff that they can do based on their role. So what does all this mean for software development? Well, one of the things we see is passwords are not great. And we know that, right? We know passwords aren't great. You forget them. You write them down. Or you forget them. Or you choose bad ones. Or you forget them. There's a billion different things that go wrong with passwords. Most of them being you forget them. Other ones being you choose bad passwords. Okay? It's probably better, for a lot of reasons, to use things that we don't have to construct ourselves, but that originate from something that has some kind of natural randomness or irreproducibility to it, like tokens, fingerprints, the pattern of blood vessels in your eye, right? Things that are consistent, that we can use, but that have a lot of randomness, a lot of information in them to make them secure. And this, in addition, reduces friction, because what do you do with your password? You forget your password. So if I can use my face or my fingerprint or something else to authenticate, that may reduce friction and still maintain a high level of security, but not cause all these other attendant problems. You should harden authentication functionality, right? Convert your passwords to something else, hash, a token, or something as soon as you get them, right? Someone logs in, and you immediately hash that password, erase it, destroy it in memory, override it, and be sure that the code gets through the compiler. Override it in memory, and then you can use that hash or something else later on as you work forward. Be sure to rate limit authentication, right? We saw that when we talked about the Girl Scouts coming to our door. Rate limit authentication requests so you protect against automated attacks, okay? And then this last line is maybe the best. There are lots of good authentication libraries out there. You don't need to implement your own authentication. You can go get one of these libraries and use it, because then you'll find that people have put a lot of work and thought and effort into it. Are there vulnerabilities in those libraries? There absolutely are. But don't roll your own. Don't roll your own crypto. Don't build your own authentication libraries. You don't need to do that. And people have spent a lot of time thinking about it and improving them and making them better. Go and use one of the ones that's out there. Don't reinvent authentication unless you really have to for some reason. And all of this together, the idea of the perimeter and the threats being inside my network and authorization and authentication and all of this takes us finally to the end of our journey and zero trust. Don't trust. Verify. So that's the basic principle of zero trust. Try to never trust and always verify. Now, clearly that's, again, aspirational. We're going to have to trust something at some point, right? A database that holds passwords, something, we'll have to trust something. But try to minimize trusted things and maximize trustworthy things, right? That's the principle we're trying to get to. So we might ask, does Aisha still work here? Is that person even Aisha? Is computer X running a trusted operating system? Is it up to date with patches? Is it running AV and endpoint protection? I'm getting dinged by this constantly at the lab. Like, your machine is turning, orange because you haven't updated your OS. Is a user authorized? And you might ask a little bit later on, are they still authorized? Because things can change. All right, what about now? Every action that you take needs to check authentication. The person doing it, we know who they are. The machine doing it, we know what it is. And authorization, right? The person in the machine is allowed to take this action. You have to check those for both. Implement least privilege. Okay? Least privilege, right? People be needing to print, so let them print. But does Amina really need access to the office on weekends? Unsupervised? With a box truck and a bunch of assistants? Something may be going on with that. I don't know. Maybe she does, but this is something I really should ask about, right? Not everybody needs that. So I need to figure out what is the minimum set of privileges I can give out so that people can do their work, do it comfortably, and get it done while still restricting all the privileges so that we don't have as much risk. So we can use privileged access management, PAM. Management, logging, and oversight of privileged accounts is what we're looking for here. If your account has special privileges, you get to write to certain stores, you get to access certain data, you get to use certain devices. Maybe you're allowed to come in remotely on a certain machine. We need to provide oversight of all that to see how that's being used. Number 3, this was in bold, assume the threats are inside the network. Assume that is true. Okay? We talked earlier about, the first rule of handgun safety is assume all guns are loaded. The first rule of network safety is assume all networks are connected. Here we go. Another basic principle. Assume you've been breached. Assume the threats are now walking around inside your network. Plan for the worst case scenario. Develop incident responses and disaster recovery plans. Don't just plan and develop and write these things down, share them with others, and critique them. Don't just do that. That is not enough. You will fail if that's what you do. What you have to do is practice them. You have to do it. You have to say, okay, let's assume the following has happened. You, who are you going to call? You, what are you going to do? You, what software are you going to run? Are you going to unplug it? When are you going to unplug us from the internet? What's going to happen? When will you call the vendor? All right? You have to practice this stuff so that everyone has in their head a way to respond to this, because it's going to happen. And the time that you don't want to be trying to find this big stuffy document and try to read it is when you're having a bad day. So operationalize these principles. Let's talk about zero trust at the federal level. So in May of 2021, President Biden issued an executive order. The executive order was about improving the nation's cybersecurity. Okay? And it's got a lot of stuff in it, but in particular, it mentions zero trust architecture 10 times, right? Clearly, something about this has crept into the brains of the people at the federal level, and they are pushing this down. And you may say, well, I don't work at a national lab. I don't work for the federal government. This doesn't affect me. It's going to, right? It's going to affect state governments, municipal governments. Oh, you don't work for those? Fine. You might work for a company that wants to be a government contractor. Ooh, now we're getting you, right? Because that turns out to be a lot of folks. Or maybe you want to be a supplier to a company as a government contractor. Pretty soon this is going to get you. So we need to figure out what is meant by moving toward zero trust architecture, right? They're insistent on it. What does that mean? So the good thing about it is there's now this explicit realization that threats are both inside and outside the network boundary. And there's this notion that we need to eliminate implicit trust. In fact, over on the right-hand side, they talk about continuous verification of the operational picture. What's happening on the network right now using real-time information from multiple sources, right? Multiple sensors are deployed, you're gathering the information, and you're figuring out what's happening, okay? Advocates of zero trust tend to believe that prior models were flawed because they were based on keeping things out of the network and defending a perimeter. And I think they're right. I think that was never practical. Okay, where did the threat to the, threat in quotes, to the time-sharing system come from? It didn't come from outside. No one out in the world knew how this system worked. They couldn't have hacked it if they wanted to. It wasn't even network connected. It came from inside with people who understood it. The threats are always going to be inside the perimeter. Yes, there are threats outside. Yes, there are bad actors outside trying to get in. Always. Defend the perimeter. Fine. Put up firewalls. Do intrusion detection. Do intrusion prevention. Great. But accept that threats are going to get into your network. You need to detect them. You need to respond to them. And you need to have plans that you have practice on how to do that. All right. All this is great. Sounds good in theory, but it doesn't tell us what to do. What do I do? Do I buy a product? Do I add a rule to a firewall? What are you making me do? Right? I need more information. And if I want to write applications that can operate in a zero trust enterprise, I probably need to know something about that, because my application, let's say, is going to have file print. Will that just work? Or do I need to have something special now because I'm living in this zero trust world? Is that handled for me by other software, or is it not handled? Right? Do I need to be able to have my stuff connect with an external data provider? I mean, maybe I do. I use a few little note-taking apps on my iPad, and they're like, oh, where are you going to put your notes? You put them in Dropbox? You put them in Box? You're going to put them over here, or over there, on the machine itself? And those things require authentication, and so now I'm having to build my app so that it's savvy about authentication to Dropbox or authentication to other data providers. Okay, so this has implications to how you build apps. Ultimately, we're going to need definitions of terms, reference architectures, structure. We're going to need to know what to do. And that takes us to NIST 800-207. That's a standard produced by the National Institute, the U.S. National Institute of Standards and Technology. And that tells us a little more about what it means to be a zero trust architecture. And this is what's being referenced by the Presidential Policy Directive. Remember, the Presidential Policy Directive comes out in 2021. This comes out in 2020, so it comes out before that. And it defines zero trust architecture, and it provides standardization of the approach and the language, etc. But the authors recognize it's not a one-size-fits-all kind of thing, right? You may be an application developer, and you care about certain parts of this. Maybe you're a system integrator, and you care about different parts of it. Maybe you're a network vendor, and you care about other things, right? There's a whole bunch of different views of this elephant, and we have to be able to understand how they can play together. All right. This document lays out a set of basic tenets for zero trust. Before, we had 3 principles, and they were pretty straightforward. Now we're going to come up with these basic tenets that are hopefully going to help us. The first one is, all data sources and computing services are considered resources. So, okay, what does that mean? How do I operationalize that? Can personal devices access my system? Can I send an enterprise originating email from my cell phone? Can I send from my cell phone email as Oak Ridge National Lab? I can. I can complete my time report on my cell phone. Feels like my cell phone, even though it's owned by me and not the National Lab and not the Department of Energy, feels like it's a resource under this definition. So this basically says, hey, the things you need to think about are broad. Maybe you don't own all of them. Maybe you don't control them all. Maybe you don't always control them. Maybe you only control them sometimes. Okay? All communication is secured regardless of network location. Yeah, you're inside the perimeter and you want to talk from box A to box B, but you know what? We need to treat that connection as initially untrusted. The basic principle is that your location inside or outside the perimeter doesn't imply trust. Okay? Access to infrastructure, you need to meet these set of requirements. Okay, regardless, to access a certain resource. We need to define what those are and then verify that you meet them, whether you're inside or outside our perimeter. Access to individual enterprise resources is granted on a per session basis. What does that mean? Well, that means, I don't just authenticate once and I'm done forever. It means that I may have to establish trust every time I want to authenticate to a resource, good use of password managers, or I may have to re-authenticate. So some of the machines I have that are on the lab network, they actually have a tool that runs where you authenticate to the tool. The tool then manages that from then on. So it saves you from having to log into a bunch of other systems. But I close the machine up, I go somewhere else, I open it back up. Maybe I have to re-authenticate now because I've broken that chain. Okay? I've changed the session. Access to resources is determined by dynamic policy. It's not a static policy that says, oh, you're in this group, boom, you get these permissions. This includes the identity of the user, the machine, information about the network connection, observable state, zombie alert level, time of day, all these things we talked about before. They need to go into determining whether or not you should have access to a particular resource. That makes this complicated, right? It may be computational, but it means that computation has to happen somewhere. So I want to mount a network share. And there's some information that says that an adversary is trying to get access to that information. And so I make the real-time decision that I will block access to that share until I know more about what's going on. I have changed policy dynamically, and that may break some people's stuff, but it may also prevent the adversary from doing harm. I have to be able to account for that dynamic change. Okay? Where does that happen, right? It's not part of all the protocols I'm using. That has to happen at some higher level where there's information that lets me enforce that policy. No asset is inherently trusted. All assets are monitored, and their integrity and security posture is measured periodically. The laptop I have for the National Lab, it has self-monitoring software on it. All my machines at the lab are periodically checked. They mark them as, I think it's orange when they need to have changes made. They can be marked red and then kicked off the network because they don't measure up to what we want as a security posture for a machine allowed to access. Same is true for me, right? Same is true for me. They need to monitor me and be sure that I'm not doing bad stuff, right? That might include stuff like periodic drug testing. That may include stuff like, pulling information about, occasionally, if you've got a clearance, pulling your credit report. These kinds of things. So we need to be sure that everything is still the way we want it to be because things change dynamically. Okay? Are there vulnerable libraries on your machine? Do you have a vulnerable version of Log4j? Oh, I may need to kick your device off the network until you fix that. Okay? So authentication and authorization, usually abbreviated AuthN and AuthZ, are dynamic, and they are strictly enforced prior to any access. Right? We said this before. Authorization and authentication checked at every session is created. Different ways to look at this. Implement identity, credential, and access management, ICAM. Implement multi-factor authentication, MFA, and do this for all resources. If you'd like to know about what ICAM means, there's a link at the bottom for it. You don't have to be digging into all the federal standards for that. Just be aware they're there. Multi-factor is what you're typically going to run into in most places. Policy can require re-authentication and reauthorization during a transaction, right? Just like my password manager is set up so that periodically normally it uses my face. I look at the camera, my password manager unlocks, and I'm good. Periodically, it will stop and say, you know what? No, enter your password. Do you remember your password? Enter it. So, again, the policy has to take all this into account, and there has to be some higher level thing that's managing this and logging problems and anomalous behavior. Collecting all the information about your assets, network, and security, right? This logging, you got to have that. Comprehensive logging, pulling information from all your assets, storing that data in a tamper-resistant manner so I can't go and mess with it and spoof it. At the lab, we do that. We pull log files from all the machines across the lab. We aggregate it. We can search it. We can look for patterns in it, etc. to protect the lab. Wow. So these tenets, there's a lot going on there. And there's a lot that feels like you need higher level structures to implement and enforce this, right? What's going to gather logs across your network? That's not a natural thing that's necessarily part of an OS deployment. So the tenets do expand on the three principles, but they imply a lot of pieces that have to be implemented and coordinated and built and have to work together. And if I buy from vendor A and vendor B and vendor C, are these things going to work correctly in that world? There's a lot of information here, but there's still not much about how do I do it? What do I buy? What do I put into this network port? What do I plug in? What do I plug it in? And that takes us to the NIST reference zero trust architecture. I mentioned they had a reference architecture. And you need one because a modern zero trust architecture is a complex assembly of components, and they have to work together, right? They all have to share data, share decision making, collect the right kind of information to enable dynamic decisions, etc. Requires maintenance, observation, right? You got to pay your IT people more. We're going to go through the reference architecture from the NIST report, but I want you to keep in mind this is an idealized realization of it, and your mileage will vary. Here's what it looks like. And yeah, one of the first things to notice, which hopefully you immediately said when you saw this, is, wow, there's a lot of boxes. Computer science is a study of boxes and arrows. Lots of boxes and arrows, so that's good. We know it's computer science. But then there's dashed lines, and there are labels on things. There's a lot going on here. And this is just the core zero trust logical components. There may be things on there you immediately recognize, right? Subject, system, enterprise resource. Great, I know what those are. PKI, public key infrastructure. Oh yeah, keys, managing keys. Okay. SIM, right? That's your event handling system, typically located in your SOC, your Security Operations Center, that collects all these events and presents them to the security people. All right, I get what that is. Activity logs, okay. Some of these things I recognize, others I might not. Let's go through them and see what's in this picture. One of the first things to notice is that we've divided up the world in that middle oval or lozenge has a red line a little below the middle there that divides the world into a control plane up at the top and a data plane down at the bottom. What's the control plane? The data plane looks subject, system, enterprise resource. There's that policy enforcement point. But for the most part, I recognize stuff there. What's in the control plane? The control plane provides communication among the different pieces. The control plane is where the decisions happen. Remember I said it was implied that there's this higher level thing that is managing these accesses, that is implementing this dynamic stuff. That's this control plane, and that's where the policy engine and that stuff lives. That's something new. It was not there before. It's something new that was added to enable zero trust. Down at the bottom is the data plane. The data plane is, for the most part, your ordinary network. It provides communication of application data between systems and resources. It has that policy enforcement point. We'll get back to that later on. The data plane and the control plane need to be logically separate. And what I mean here is, suppose that I, within the data plane, can go into the policy engine and make changes. That's a problem. Right? The policy engine is there to control what's allowed to happen in the data plane. All right? And so I need to enforce that hierarchy. Right? The policy engine, the policy administrator, and the PEPs, right? Policy enforcement points, communicate on a network that is or should be logically separate and not directly accessible by enterprise assets and resources. Logically separate is different from physically separate. I'm not saying you got to pull a bunch of new Cat 5 in the walls. We can make them logically separate by having that traffic ride over the standard network using its own encryption. So let's talk about the pieces around the outside. These are all things that feed into the policy engine and the decisions that are made at the policy enforcement points. The first one is this CDM, Continuous Diagnostics and Mitigation. This is where we determine, is your computer patched? Is it got a trusted OS? What's going on that machine, right? Are there known vulnerabilities? Should I restrict it in some way? This provides information about the asset making the request, the access request. Okay? Next is industry compliance. Maybe you're in healthcare. Maybe you're a defense contractor. Maybe you're an insurance company. Maybe you're a finance company. There are special rules in many industries that apply to you. They say you can do this, you can't do this, you should do this, you shouldn't do this. And you're like, well, should and shouldn't sound squishy. Maybe I'll ignore that. But you will probably need insurance, and your insurer will probably ask, why didn't you follow this industry best practice? It said you should do this. Why didn't you do it? I didn't feel like it. Well, we're going to deny your claim, right? So there's things you have to do, things you should do, and those may have to do with which industry you're in. You need to assure compliance with the industry standards, especially with whatever the prevailing standard is in your industry. Threat intelligence, right? Data comes in from a variety of sources. There are threat intelligence companies. You can contract with them and get a feed of information, depending upon whether maybe you have someone who has a clearance on your staff. Some large energy grid transmission authorities have people with clearances. They can get threat intelligence that may be classified. There's open source threat intelligence that comes down from companies, right? They tell you, hey, we're seeing the following. You should maybe put in a firewall rule, or you should put in a detector or a sensor for this because this is going on right now and you may be targeted, right? That's great stuff. That's helpful for me to defend the network. So I get a feed of threat intelligence. I get activity logs, right? I find out, why is Aisha here on the weekend with a box truck, right? I see that on the camera. I see it on the door access logs, etc. Okay. And this is important. Maybe I don't use this in real time. Maybe I do. Maybe I use it in real time. Maybe I don't use it in real time, but I use it after the fact to discover that there has been a problem and to figure out how that happened, to diagnose it, to report it up to my threat intelligence partner, and to protect myself in the future. Data access policies, right? These are the rules that could be static or dynamic that allow you to access or not access resources like printers and file shares and all that kind of stuff. Public key infrastructure, right? The thing that drives everyone nuts. The policies and the system for generating and managing certificates and keys throughout your enterprise, okay? Could be federal PKI, could be your own PKI. There could be air-gapped systems in there, right? Air-gapped being a myth, but you could have a system you think is air-gapped to generate signing certificates. And you should make an effort to try to make that system as air-gapped as possible. ID management, right? User accounts, adding accounts, deleting accounts, right? We've got to manage all of that somewhere. Adding and deleting machine accounts like on domain controls. We got to manage all that somewhere. And then your SIM, your security information and event management system, that collects and presents security information for later analysis. Maybe it's feeding that into an Elasticsearch database. Maybe it's doing something else. It's feeding in some other visualization tools. Whatever you're doing with that information, we're feeding that information in as well. So all of that comes together. Within the control plane, there's a policy engine. And the policy engine is there to do just what you would guess, to enforce policy, right? We've set up policies. We've said people in this group can access these resources. People in this group can access these additional resources. In addition, if the following things are true, if the following conditions are met, you can access this stuff. Great. So we create a set of policies. Okay? We have to be able to manage all of this. The policy administrator then executes the decisions of the policy engine. Okay? It can allow you to establish a connection between a system and an enterprise resource, or maybe it can shut that access down based on dynamic changes in policy. The policy enforcement point lives at least partly down in the data plane. You notice the dashed line cuts it. That's intentional, right? The policy enforcement point talks to the stuff in the control plane, so it's partly in the control plane, but it also has to be able to interrupt these the stuff going on the data plane. Typically, this lives on your system. This is a piece of software on your system that communicates with the back end to determine what we should or shouldn't do. It's a local gatekeeper on your machine. Now, that was the reference architecture. There are implementations. You can go out and buy an implementation, right? Perimeter 81 has their software-defined perimeter. Beyond Corp is out there. CrowdStrike, our old buddy CrowdStrike. I feel like I've heard that name somewhere. Cloud-native zero trust that adheres to the NIST 800-207 standard. Great, that sounds perfect. Let's go get us some CrowdStrike, right? These are all out there, and there are many others coming. So the zero trust architecture operationalizes, right? It puts into practice a lot of the security principles we've been talking about. But if it's not managed carefully, it can itself become a risk. How could that happen? I'll go back a slide and just mention CrowdStrike. Okay? You have to be aware that all of this stuff we talked about, this is additional stuff. This isn't whatever your business is. This is stuff you're building around it. All that stuff has vulnerabilities. All that stuff has problems and bugs in it. And maybe the way the bad guys get into your network isn't because you've got bad code or you've got, bad stuff on there. Maybe it's because there's a vulnerability in the systems you're using to protect it. So keep all that in mind. And now let's talk about application development. So are there implications for software development? Yeah, there are, right? We need to think about the network. We need to think about authentication and authorization, and we need to think about threats. What do I mean by this? Think about interactions in terms of sessions, right? Each session being subject to authentication and authorization, and your system should be prepared for when it has to re-authenticate and reauthorize to continue some process, right? Maybe you're transferring a big file, you're doing something that takes a long time. In the middle of that, you might suddenly be asked, hey, re-authenticate, and you need to be able to respond when that happens. Determine the attributes for zero trust, right? The authenticated identity of the user, the status of the device, the application, function you're using, so on. You need to be able to marshal that information. And treat every session as originating outside the trust boundary. Okay? There we go. And there are some implementations at the bottom. Primitive 1, CrowdStrike Zero Trust API, or 2. Authentication and authorization. Apply additional security measures like segmenting your application, right? Adding enforcement of compliance controls. Adding logging. Using multi-factor authentication within your application. And there are things that help you implement that. AuthZ and Okta are 2 that I'll list here for doing that kind of stuff. Default deny, right? Make sure that at all stages of an application lifecycle, we only grant access if it's explicitly allowed, right? Our default condition is to say, no, you can't do that. And you have to then prove to us that you should be able to do it, and then we say, okay, then you can do it this time, and then repeat. You've got to then re-authenticate each time you want to do it. Okay, these are all application concerns. Threats, right? Adding APIs, even adding security APIs, expands the attack surface. There are 2 kinds of things that are present in these APIs. There are latent weaknesses. These are weaknesses that are always present because of bad coding, and we don't know they're there. They're bugs that are there. Are there latent weaknesses in, let's pick a random piece of software, are there latent weaknesses in Microsoft Excel? Yes. An explicit weakness is a weakness that is known and that is based in the configuration, structure, and policy of the system. We can know about it, right? We know there is a weakness. And maybe knowing it's there, maybe the vendor fixes it, or maybe it's going to take time, and we have to then work around it. We have to turn that weakness into an unexploitable weakness by adding protection around it. Adding all that layer of protection around it, that's going to add latent weaknesses, but those are latent. They're not known, right? The difference between latent and explicit is latent is the 0-day stuff. Explicit is the stuff everyone knows about and is actively exploiting. Okay? The punchline to this is adding stuff always increases the latent weaknesses, but might, we hope, decrease the explicit weaknesses. And that's important. We saw that, right? 0 days account for this vanishingly small and shrinking percentage of all attacks. Most of them are targeting stuff that people know about because that's easier and people don't pass stuff fast. So we may increase the latent weaknesses by adding this stuff. All right, we accept that. We accept that as the cost for decreasing the explicit weaknesses. Adding zero trust components to, or even microsegmentation, also increases the complexity of the application, right? Now, I got more stuff going on. Just like if I segment my database, I put the user information over here, the credit card information over here, the health information over here. A simple query, I may have to query all 3 of these. It's way more complicated than if I just put them all in a single database, right? I've increased the complexity, but I've done this so I can reduce my exposure. I can manage my attack surface. I can hopefully reduce the explicit weaknesses that are in my system. All security is contextual, and implementing security always involves trade-offs. That's just a fact. If those 2 things, put them in your brain, all security is contextual, and implementing security always involves trade-offs. And that's it.